Good morning, everyone. What am I going to talk about here today? Because this is a performance track. It may seem a little bit odd to talk about protocols, but I'm going to cover with sort of two major things to begin with, which are kind of interesting. First thing is code. And probably not the code that you think, but the code that we write is encoding something else, usually. So I'm going to cover a little bit of that. And it's the way we do stuff, the way we behave, the way things interact. Like, there's interesting codes that we have, like what is the code to make good coffee, I find. Like you go to Tuscany or anywhere in Italy and you get amazing coffee, go to a hotel anywhere in the UK or pretty much in the US and you get coffee that's disgusting. Maybe they make coffee a bit like this. Is this the correct protocol to go make coffee? Well, actually it would kind of work. And that's kind of like most of the code that I get to see in production. People kind of make stuff work. Kind of questionable. Is it the right way to do it? So I want to kind of talk about protocols, really. And I'm going to sort of say that I think protocols are one of the most significant discoveries of sort of human history. And at the end of the talk, we'll come back to that and see if we kind of agree with this or not and some of the points around it. So protocols, what are they about? What sort of things are we thinking about here? So as a word, what does it mean? Well, we're talking about a code, yeah, okay, we kind of get that. That's describing a strict adherence to an etiquette or precedent, etiquette and precedent together. And particularly the precedent side I find is so important in code because precedent is all about timing, the order in which things happen. And as we get into concurrent and distributed systems, the ordering in which things happen is very key to making that work. And so how do things behave? Etiquette is really about kind of behavior. I'm going to explore this in some detail. From a computing perspective, it's also described like this, a set of conventions governing the treatment and formatting of data. Often people just think about the formatting. It is an important part, but it's only a small part. The treatment is actually way more important, and treatment is about etiquette and precedence. We're going to kind of go into that. But before we get into some of the computing stuff, I want to talk about a little bit how we've evolved as humans and what we have kind of learned. I find this subject kind of fascinating because I find there's so much to learn in it from myself as well. And kind of going back, I started studying this, and there's a lot of sort of origin in evolutionary biology, where we come up with protocols, where we come up with etiquette, manners, all of that sort of thing, and how it influences what we do. Interesting things, like go right back to things like facial expressions. Charles Darwin, like we know his work on things like origin of the species, but he did a lot of other things, like looking at how different societies evolved and how we sort of communicate and learn. And there's some real innate things that don't require teaching. People know this without it being taught to them around how we recognize things. Like we recognize shame, we recognize disgust, regardless of language, even if someone has never been taught language. And there is incidences in the world where people have unfortunately had a feral upbringing, they were never introduced to language, they still understand things like shame and disgust. Because we sort of get that. We see this in other things, like I love dogs, I've interacted with dogs all my life. It's really clear, dogs know shame. There's some things that are kind of innate in what we do. So there's things that we can learn from this. And does it work in code? I've seen a lot of JavaScript, and it's pretty disgusting. So we can definitely learn from some of these sorts of things. Then it's kind of evolved, so it goes much further. So that's the real sort of core biology stuff. We have taken this much further. We're kind of the smart apes that exist in the world, and we've taken it through things like etiquette and manners. And this is actually really interesting where we start to form protocols around doing stuff. So the etiquettes around things are very interesting. There's three types of manners that come out from etiquette. So at a base level, we have what are known as the hygiene style manners. And that's all really base level stuff that's important, mostly about the prevention of disease. So a lot of this sort of shame and disgust and different things come about from that is where we teach people around things that will help prevent disease. It's also things like how close we get to different people, this sort of public space, personal space, intimate space. You don't involve people, sort of go into people's intimate space, mostly because it prevents the spread of disease. We've evolved in certain ways to do stuff. And then there's ways we relax some of these rules. So going on from the hygiene stuff, we then have the courtesy side of things. This is how we sort of bond and create societies. And this is kind of being polite is one way of thinking about it. Like, so someone else can eat before I eat, What you're saying there is, you're saying that the society is more important, the community is more important than me as an individual. And we learn these things because actually our individual survival is based on survival of the society. So you start to see how things should behave around that level. And then it gets more advanced again with like cultural norms. So people all behaving in a similar way, you identify as part of a group. And what that does is it builds trust. And then certain other things can be relaxed. So you can relax some of the more strict things you would have around boundaries, mistrusting other people, and you make things more efficient. So we've evolved through a lot of these sorts of things. And as we got more advanced as a society, we start to use them in interesting ways. So one of the very common ones that is sort of well documented and well understood is the military. And we have very strict protocols around how we go to war, how do we act in the cases of wars. This is known as the rules of engagement for anybody who's had any military experience. And you'll see it's all about what is acceptable whenever you go to war, because war should be considered as a last-ditch attempt to do something. I seen a great talk with a guy called General Mike Jackson a number of years ago, and he said, the point of war is not to defeat or crush your enemy. The point of war is to change someone's mind. It's whenever you've got a disagreement, it's the last thing you do before trying to change their mind. It's the ultimate thing you can do, but it's the only thing that should be done as a last resort. Talk about the good conditions to succeed. If you look at the laws that surround this, they fall into two groups. This is the jus ad bellum and the jus ad bello. And what is the first one is the Latin term for the right to go to war. There's a strict protocol you should follow before you start a war. And that's things like you must go through diplomacy, you must behave in a certain way, and then it's a last-ditch attempt. If you don't follow those, there's a difference between being a soldier and a murderer or a criminal. The difference between murder and war is, do you follow these laws? So it's a strict protocol around this. And so there's a lot to be kind of learned about how people have done this. And by doing that, they end up behaving in better ways. So if we cause less damage, we do certain things. Like examples in this is like, so things should be proportional. If you're a superpower that has nuclear weapons and somebody happens to blow up one of your ships, you don't retaliate and nuke their capital. That is not acceptable as behavior. You're supposed to be proportionate. And then if it escalates, you're still within the law. So it's kind of interesting. So a lot to be kind of learned from our history in this. So let's go into concurrent and distributed systems. How does some of this start to go through, and how can we apply some of it? Because it might seem a bit kind of high level. Well, fundamentally, we're talking about is how do things interact. And this is really the whole essence of when we write code, is we are encoding how things interact. And getting that right makes a big difference to the quality of the given output. Like, we've evolved as humans with all of these protocols because we want a certain quality outcome. As an engineering discipline, we're very young, we're very immature, and we're kind of working some of this out. So what can we do to kind of get a bit better at this, and what can we learn? There are some bodies out there that have done really great work in this space. The IETF is probably one of the best examples of this, where we very strictly document our protocols. They're known as the RFCs typically, and we follow those, and this allows us to create great things like the internet. We wouldn't have the internet without the RFCs that describe the protocols for what we got to deal with. Now, kind of coming back to coffee again for a second. How do we make coffee? Like, the IETF has even got a kind of a fun thing that happens. Like, on the 1st of April each year, they usually release an RFC that describes something interesting. This particular one was a hypertext protocol for controlling a coffee pot. And they produced some of this, and it's kind of fun. And some of the bits is like, you can return a 418 to say, I'm a teapot, rather than I make coffee. So that's the kind of fun side, and they do continue on. There's various other examples of this. Some of them are fun, but also really informative. Like, everyone heard of Big Indian and Little Indian as a way of encoding integers? This paper is the best description I have seen of it anywhere, and it's one of the 1st of April papers that come out from the IETF. So back in 1980, And if you haven't read this, you actually discover the origin of why we call it Big Indian and Little Indian. And it's to do with Gulliver's Travels, Lilliput, where the people there were divided and had different views. And so how do you have societies believing in different things? Well, what they believed in was one group said you eat your boiled eggs by smashing the big end, and the other one smashed the little end to get into the egg. And that is the origin of Big Indian and Little Indian. It's the endian of the egg. This paper describes the origin of that, but it also describes why we do it with memory and the kind of interesting stuff around that. So that's kind of cool. It's a way to sort of learn some of these things, but also have a bit of fun at the same time. Like various other examples, it's like, how do we do IP over avian carriers? That was kind of there. That was expanded with how do we add QoS to that? So we've got quality of service. We can take that a bit further. And just recently, we updated it to make sure we've covered IPv6. So this sort of stuff's in there, kind of good fun, sort of interesting. How do we make this a bit more practical for ourselves? Particularly, how do we document our protocols? I find this is actually one of the really good things you should do when you're working on any project that's of any sort of complexity, is start documenting your protocol. And kind of what do I mean by this? Well, you can hear about APIs versus protocols. I think APIs are a very one-dimensional, very anemic view, and protocols are a much better way of thinking about it. So when people talk about API design, that's a very narrow dimension of it. But it's not complicated. So for example, let's say I wanted to write the protocol for how to use a file system. I want to use a file. It could be as simple as I open a file, I can perform 0 or more read or write operations, and I close the file. Now that's a kind of pseudo-regular expression style syntax. I've seen some people use extended Backus North form. There's other ways we can do this, but I kind of like this as a way to do something. It's actually pretty simple. And notice it tells you the precedence as well as what operations are available there. An API does not give you the precedence for its usage. And that's really important. So you end up making a lot less mistakes when you've described the precedence. And then you go on and you expand it and you say, okay, what is a read operation? What's a write? What's an open? These sorts of things. By just doing that, it really improves the quality of the component you're developing or the system you're developing. You now know how you should interact with it. And that can just be a piece of ASCII that's there sort of documenting your component and how to use it. That's usually how I start with most of my distributed systems or concurrent systems I work on. I put something like that together. I flesh out so much of my own thinking by doing something as simple as that. And then what you do with this, well, just think what are the events that are happening in your system? What's the pre and post conditions? What are the invariants that are going to hold true whenever these things occur? And just document it. Write it down in text. You're encoding what your protocol is going to be, and then later you will encode it in whatever your preferred language is. Hopefully not JavaScript, otherwise you see the disgust again coming through. Well, and particularly in the disgust, think about what can go wrong. Besides writing it in JavaScript, Todd Montgomery, who I get to work with a lot, this is one thing he's taught me that's such an important thing in designing protocols. When you look at any step in the system or any interaction that's going to happen, is what can go wrong? Always answer that question, or ask that question and try to answer it. Todd has written lots of software that was involved in sort of space explorations. He worked for NASA and different things. And just you have the mindset, what can go wrong? And this is where I think things like RPC is so broken. Most people just assume it's going to work. That leads us down a wrong road, where you sort of think, it's asynchronous communication, I'll send a request, I'll maybe get a response back. What can go wrong? You may not get the response. That should be a normal thing that you think about. How do you deal with it? How do you time out? How do we do things in an interesting way? So very, very simple examples. Let's make it a bit more real and show a reasonably interesting, complicated example. So let's say I want to build a system. Say it's a whiteboard or a chat room or just something around to share lots of information to a large number of users. Multicast is a really nice way to do that. So I'm going to send the data out from a source to many different receivers. Now, we can implement that in a number of different ways. If we did it with TCP, one of the problems is it doesn't scale. If you do it that way, you end up having to send the data to all of the different receivers and handle acknowledgement back from all of them, so you get a problem of all of this traffic exploding up. Multicast is kind of nice because you can send it once and all the receivers get it. But we've got some issues with multicast and UDP in general. It's not reliable. How do you know if you've lost data? Well, do you use an acknowledgement protocol? If you start acknowledging back, that doesn't scale up either, because as you add numbers of receivers, it doesn't scale up, because we're dealing with too much data coming back. So we take a different approach. Is we won't just acknowledge, we will negatively acknowledge. So just send a NAC when you don't get data or data arrives out of sequence. That way we can scale up much better, because you're going to rely on the fact that loss is going to be a more infrequent event than successful delivery. That's a different protocol, a different way of thinking, but it's got some issues as well. So we get this, either we have an ACK implosion, but we can also get NAC implosions. So let's say you send from the source, and most times when you have loss is correlated with some event. Like, I have overrun a buffer at the source, I've overrun a buffer at the network switch that's then going to distribute this data. Once you've done that, you now have some loss. All the receivers are all probably likely to experience the same loss. So if they go to NAC, they all NAC at the same time. The source gets all of those NACs, huge amount of NACs. It then goes to send all that data multiple times to all of the different receivers. And now we've got a meltdown scenario, because all of this data goes out. That floods the network. You've probably got a loss problem in the first place. Now you've got even more data in a feedback cycle, and you get into what's known as NAC implosion or congestion collapse. These sorts of things end up happening. How could we deal with that better? Well, there's some really interesting work in this space, like going back to the 1980s and slightly beyond that. One of them is a nice paper by Solly Floyd. So Solly Floyd worked with Van Jacobson and sort of rescued a lot of the internet in the 1980s. We suffered from a thing called congestion collapse over TCP. And they brought in congestion control to TCP and really improved things. Solly's other great contribution is some of the work here, where what ends up happening is, when you go to NAC, how about not everybody NACs, not everybody screams at the same time? So let's say something goes wrong in the room. If everybody screams it's wrong, it's just too much noise. What if, say, you notice that something's gone wrong, and you decide, I'm going to wait a little bit of time to see, has anybody else noticed it first? Just a reasonable little bit of time, and if somebody else raises it first, I won't raise it as an issue, because it's fine, it's already been dealt with. She encoded it in this algorithm by doing this. So what you do is, if you get loss, you set a random timer for a very short period of time in the future, related to how long it takes for communication to happen, so quite a short period of time. The random timers are going to go off between now and this given timeout in a sort of normal distribution. So the first one to go off will end up sending the request to get the data sent again. The data will be resent. And because it's multicast, it's sent to everyone. Then whenever the others have seen this data, they know that they don't need to send the NAC themselves, because they've already got it, so they just listen for the data to be resent. Now we've only had one or maybe a small number of NACs, and we've dealt with all of this data. Nice, simple, clean, no central control, using random timers as a way of doing something. Beautifully simple algorithm. Scales really, really nicely. I think that's a really interesting way of thinking about the problem. To me, that's the essence of really good protocols, especially thinking about how a group or community of entities, whatever they happen to be, in this case happens to be computing nodes that are saying that I haven't got the data, they're behaving in a really nice, interesting, coordinated way. And this ends up scaling quite nicely. But that sort of thinking then inspired some other people. Now, this was done with a normal distribution. And what happens is, with a normal distribution, you still can get clusters of NACs. You can get quite a lot coming along. So you end up with a thing called NAC suppression needs to be added to that algorithm to dampen it out a little bit more. Someone had a good idea of what, we'll change this. So rather than doing the timers firing with a normal distribution, if we change the distribution to be an exponential distribution and we truncate it at both ends, we get this really nice, interesting property where the bulk of the timers are going to fire later in the cycle, but we're going to truncate the lower end, and with reasonable numbers, and you set the sample sets correctly, you will likely get a timer to fire really quite soon, but you don't have to suppress stuff because there's very little NACs flying around. This ended up being a really nice improvement on that we end up getting even lower latency. We don't need NAC suppression, and we take a lot of network traffic away. So again, a beautiful algorithm using mathematics, using cooperation. We get higher throughput, lower latency, and a really nice, elegant solution. It's not all clever coding and bit shifting, but we get a really good solution to the thing by thinking what are the protocols of interaction. As people kind of thinking differently, I think there's some really cool stuff in here. By the way, that is the algorithm we end up implementing in Aeron, and we've been getting really great results from it. And it's such simple, elegant code. It just works really well rather than going with something overly complicated and complex. So where should we focus if we're going to look at protocols in general? Like, there's lots of things within protocols. Like, I'm not going to cover all of these, but I just want to sort of highlight, it's a really interesting, rich subject and a rich history to different things that are in there. I'm going to pick out a few of them and sort of show, like, well, how do they impact how we interact? How do we learn from that? How do we make some of our code a bit better? So since we're in a performance track, I'm going to give you the one tip that will make the biggest difference to your code from a performance perspective. And that's when you come to the encoding step, please don't use text protocols. Use binary instead. It's the single biggest thing you can probably make as a difference. Yet we keep producing all of this JSON and XML and YAML and, disgust is going to come out of me again. Do the people who write all of these things, are they typically neuroatypical and have no interaction skills with the world? Did they never experience disgust from the people around them as they produced this stuff? So clearly some of it has gone wrong in our interactions with these things. Like, let's use binary protocols. And when people say, no, but text is so much easier, it's human readable. Rubbish, it's not human readable. I know very few people who can read ASCII and virtually no one who can read UTF-8. You've got a text editor that can read it, and you can read that. You've got a tool that can do it. If you want binary to work, well, you write a tool to do the binary. That's what you need. It's not that the text itself is human readable. It's kind of really interesting how we contort how we think about the world. We kind of miss some of the interesting points. And whenever we do it in binary, we can go with sort of what people in IETF would call protocol porn, and we describe it in ASCII as how things are laid out, and then we can write our tools to deal with this and work quite nicely, and we'll save so much cycles in how we deal with these things. So that's the main thing on performance. I'll come back to a few other things on performance, but if you just at least do that, hopefully we'll sort of save a few more trees around the planet and people stop wasting lots of CPU time. I'm not joking. Like, I get to profile many real-world applications, and sometimes the business logic, the percentage of time spent in it is an absolute rounding error, often less than 1%, and so much is the time taking this crap off the network to eventually go through many, many, many layers of translations to eventually invoke some business functionality at the end of it. That's what we do a lot of. Let's pick another topic in here, versioning. Versioning is a kind of really interesting, fascinating one as well, and something I've discovered that my own learning and understanding of it has been sort of really advancing. It's a subject I keep finding more and more interesting things within it. And so what are we talking about in versioning? So versioning and identity can often be interlinked as well. So when we talk about protocols, what conversation are we having? That's the first kind of one of the important things that we're having. Is that when you're engaged in any conversation, any sort of message that you get, which protocol does this belong to? And it's kind of good to know that, and can that version over time? So can we upgrade stuff, keep things going? The messages themselves is, what is the version of the encoding? Is this version 1? Is it version 2? Is it version 3? We can add fields to things. We can never take stuff away if we want to have a system be up all of the time. So we can add stuff and we can expand, but we can deal with this for versioning. It all works really well. What's way more interesting, and something my own understanding has been coming forward a lot with, is the versioning of state. And this is a kind of really fascinating topic in its own right. And so what do I mean by this? Let's give some examples. Well, I've done some work on some multi-producer, multi-consumer queues, and I like to do things lock-free. The space I work in requires a lot of performance, so we are doing lock-free algorithms using atomic primitives around things. And there's some great work like Lamport, fast flow, various other stuff that's out there over time. And I've been taking algorithms that were like single producer, single consumer, multi-producer, single consumer, evolving all of these, combining some of the algorithms, doing quite well. Multi-producer, multi-consumer is a really interestingly complicated one. And you can evolve some of Lamport's work and some of the other work to get a working solution. I found that some of the ones I produced in this worked reasonably well and got reasonable performance. And then after a few years, I seen these odd bugs that would appear. And then discovered there were some flaws in my algorithm. I needed to fix it, and eventually dug into it, found out what was wrong with it, and had these sort of odd cases of where queues are particularly full or empty. At wrap cases, you can end up with ABA problems, and you get bugs in your code, and you have to fix them. And I came up with some quite complicated solutions to fix it by casing different things, and I could do an algorithm with 2 cases and some ordering rules, and it would kind of work, but was kind of uncomfortable. And then I started searching around to see, well, what can be done better? How can we deal with this better? And I came across this 1024cores.net site. There's a guy who produces this, Dmitry Yukov. He now works on the Go team. He was at Intel before, and he has a beautiful algorithm for multi-producer, multi-consumer. And I remember whenever I read it, I just thought, wow, it just made it so much easier. He does it with 1 cas, but the thing that he does that's fundamentally different is he versions everything that comes into the cube and everything that goes out of it. So you've got the sequence slot that you use, so you never get the ABA problem because everything is given its own sequence. Now, there's an interesting trade-off with that is it requires more memory to track this, but it actually performs really, really well. In C, it's beautiful because you can keep an array of structures where you've got a pointer to the object that you're putting in and the sequence number side by side. Unfortunately, we can't do that sort of thing in languages like Java because we've only got arrays of references. If we've got arrays of value types, this would be much better, and we could deal with it, keep them co-located. But you can implement it by 2 arrays where the same slot index means the same sort of thing. This was so much more elegant, but what he was doing is he's versioning the state of the interaction, because you've got producers and you've got consumers. If a producer produces something, if it's given a version ID, you know that it's the right thing that's been handed off, and you know who owns a slot at any given point in time without any locks. So kind of versioning the state, really interesting. Like another example of versioning the state is consensus algorithms. So things like Raft is the current popular algorithm in this space. We version everything around this. So every message has got a version number. So it goes forward sort of monotonically, but also things like elections. So every time you've got an election, the election has a leadership term ID and a candidate term ID that we deal with this. And this goes forward monotonically. So if you get a message that's whizzed around your network, comes back later, but it's from an earlier election, you know it's from an earlier election because it's got the version number on it. These sort of things start to matter. And then it makes it so much easier in a distributed or concurrent context to do this. I think this is one of the most important personal discoveries for me, getting some of these algorithms right. It really makes it so much easier. So kind of be aware of that. The good old sync versus async debate is really interesting, especially in concurrent and distributed systems. Let's explore what some of this means from a timing perspective. So if I've got 2 things I want to communicate together, and they're going to use a synchronous protocol, I have to send a request from one, send the response back, send another request, another response back, request, response. Time is progressing as we go with this. If we increase the latency, what happens? I can get less done in the same amount of time. We program lots of things using synchronous protocols by request response. And like, what's happening in the meantime? We end up having to send a request. We're waiting for a long enough period of time. We often block on the response, which means the operating system has to get involved. This thread has to be suspended. It has to be woken up again whenever the packet comes back from the other side. We spend a lot of time on overhead and bureaucracy in dealing with these, plus the time to deal with these sorts of algorithms. If it's asynchronous, what happens instead? So we send a request. We don't wait for a response. We can send another request. We can send another request. And then the responses all start coming back. We greatly compress the time we're dealing with this. Like in any distributed system, if you start being asynchronous, we can get so much more done by sending requests and getting the responses. Like we increase the latency, what happens? It does much better. So even as latency increases, async plays off much better. So one of the things like Todd was banging into me from before, the guy who taught me about what can go wrong, like he was writing software that was talking to things going to Mars and further out in the solar system. Latency is a real serious problem then. You do not do REST, request response, when you're talking to something on its way to Saturn. It's not going to really work. Yet we kind of have this kind of silly ways of thinking and looking at software that deals with it. And what's happening in this sort of case? Well, if I'm making non-blocking sends and non-blocking receives, is I can do other things in the meantime. So I can send the stuff, I can go off and do other things, I can come back. I teach concurrency, and I do a few courses a year. It's kind of interesting. And I've sort of been looking at what are the characteristics that makes good concurrent programmers. And one of the things I find quite common is either people who play musical instruments in a band because they're used to working with other people, and people who are good at cooking. Because if you're in the kitchen and you have to deal with multiple things all happening at the same time, if you're synchronous, you can't make anything interesting. Sort of things, it's the thinking and ways we approach this stuff, it's really interesting. But people will say, but, synchronous is so much easier. No, it's not. It's how you think about the problem. It's how you manage the feedback and how you manage the state. Using the thread stack to manage your state is a very opaque way of doing that. So you've got multiple requests going, how do you monitor a system that's doing that without doing something really weird? If you have the state model for what's going on, like proper state machine saying, okay, I'm sending this off, I send a request off, I change state. I get a response back, I change state. I don't get a response back, I get a timeout, whatever. You make all of that as part of the model of your domain and make it observable. You can now see what's going on in your system. It's not opaque anymore. It's a different way of thinking. I find that synchronous systems, you get going really quickly and then it gets really hard as complexity builds up. Asynchronous systems are a bit harder to get going initially, but then you sort of hit the same level of complexity. Unfortunately, we're kind of driven this we want instant feedback and instantly getting things done well. This is why we have problems like JavaScript, why we have problems with VB. We have to know that we have to actually do a little bit more work up front, but then we can do much better later on. We need to demonstrate that disgust much more when we see these bad practices being put into place. And we use events more, and think about it, this is the real world. The real world is decoupled in space and time. To pretend it's not is kind of crazy. Like all underlying protocols are send something off, get something back. They're asynchronous under the hood. But we force sort of synchronous on top of it. So if you're going to build your own system and your own API, at least think about this. If you're going to build something, build it with an asynchronous interface. And then wrap it with synchronous. So if you get the people who kind of need methadone and they can't get off, the bad drug habit they've got of using synchronous programming, give them this for a bit and try and wean them off it. Don't go ahead and just build a synchronous API, because then you're just locking it in and you're kind of making it worse for the future. You won't get the performance. And we can see some of this with some of the history of certain protocols and how they work. So things like RPC, HTTP, TCP. So we build, typically these days, RPCs on top of HTTP, which is on top of TCP. Really inappropriate protocols. So TCP was not designed for request response. Anybody wants to grab me afterwards and we'll talk about time wait and fast start and all the problems around TCP. It's such the wrong protocol. It's a great protocol, not for what it's being used for. We then wrap it with HTTP, which is a document fetching model. And we're using this to communicate to servers. And then we're putting RPC that we've known has been broken for years. And yet we keep doing this. Come on, please. Let's show our disgust more and stop doing some of this stuff, because it's kind of bad. So we end up trying to fix this by sort of gaffer tape and banding. It's like TCP now has fast open to try and get around to some of the slow start processes. We're now using quick. So if you use a Google browser talking to a Google service, you don't use TCP anymore. You're typically going over quick, which is a UDP-based protocol. It's much better for what you end up doing. Like we're seeing HTTP1 go through things like Speedy, and HTTP2 is available now. Also things like the encodings. We're not using text encodings anymore. We're moving to binary encodings. So people are learning this is what we need to do and we need to get better. There's some really good examples in TLS going from 1.1 to 1.2. We save a round trip time because being locked into some of the synchronous stuff is really, really hurting us. Like, go read protocols, you can find out much more about this. Batching. Now, this is kind of an interesting one. And take this back to protocol. Think about the etiquette of making a request. Like, humans do this really horrible thing whenever we want to be unpleasant to any group of society or any group of individuals, we dehumanize them. Because then that takes us away from our instincts, our protocols that come into place. We dehumanize them. So imagine you go into a friend's house and they're making dinner and you're getting involved with it and says, do you know what, I need a pint of milk. Could you run down to the shops for me and get a pint of milk to finish? It's like all friends go, yeah, no problem, let's go do this. So you go get the pint of milk and you come back again. And then they said, oh, actually, I need another pint of milk. Could you go back to the shops and get me another one? And so you go back to the shops and get another pint of milk. And then come back in and say, no, actually, I need another one. And I need a block of cheese. You're going to get pissed off with your friend at this. You're going to start showing some of those basic hygiene manners. So you're going to train them into, you should have really thought about how much you need and go get them. So thinking about it, yet we deal with computers without thinking about the interactions. We disconnect ourselves from that. And that causes a lot of really bad behaviors and things that we have evolved to deal with. We've got to think a little bit differently. And we need to for how some of the stuff's going to do. Like, can we use a 100 gigabit Ethernet connection using our current APIs and ways of interacting with it? We can't. We can't use the sockets BSD API to get 100 gigabit Ethernet working because we just can't make that number of syscalls. It becomes a real problem. Syscalls are something that is such a limiting factor in our performance. And now with things like Spectre and Meltdown, they're becoming even more expensive. So we need to work out, if we're going to use these as an expensive thing, we use them as infrequently as possible. And we batch and we think of different ways of doing stuff. For example, if you're in the networking space, if you're on Linux, for a while you've been able to do things like send a message and receive a message where you can send multiple things to the network in one system call, receive multiple things. Like, don't send the friend to get a pint of milk 3 times. Ask for 3 pints of milk. Do that sort of stuff. So think about being kind of kinder to this. We're seeing other protocols that are coming up in user space to save us these. And then we're going to asynchronous protocols. So things like DPDK, EFVI, or DMA. These allow us to get full usage of things like 100 gigabit Ethernet stacks. We had to think differently. RPC, sort of with TCP and HTTP and all that stuff, forget it. You're not going to get the proper usage out of these. We got to think differently. I like to think about it like, think about naturally batching up your stuff. Treat things with some sympathy. Think of the computer not as an inanimate object. Let some of your instincts come into play that we're designed to interact with people and other organic things come into place. So we'll do things in the right sort of way rather than dehumanizing and going the other way. Then we can get better use. And it's not to be obsessing about it. It's not like it is a human. But don't try to overcome the other things. So try to think about, like, its natural way is to write a frame to the network. Its natural way is to write a block to a disk or whatever. We'll take account of that, show some sympathy for it. Like examples of when we don't show things, like ORMs. Again, like another great source of some disgusting performance issues that we have out there, where things just aren't designed to work together. It's like, and a database, like you need stuff from a number of tables. Write a join statement, get it back in one go. And actually, SQL's not hard. It's actually quite pleasant if you bother to learn it. Most ORMs are not that pleasant if you've got to deal with them. They're pretty disgusting. I'm going to kind of wrap up a little bit here and think about things like I call snake oil protocols. And this is kind of a really interesting way of starting to look at how some of our human behaviors go. One of my favorites is two-phase commit, or XA, as it's kind of known. And this is something people often ask me about whenever, and typically these are people who are architects. And what they're doing is they're trying to make what should be their problem someone else's problem. This is bad protocol. This is the sort of stuff that we should not sort of allow in society. And there's a lot of interesting things we dig into what's going on with XA. So more great papers to look at. There's one of the ones by Jim Gray and Leslie Lamport. Unfortunately, we don't have Jim anymore. So this is only 2002 or 2004, so relatively recent, but there's a body of work showing how bad XA and two-phase commit is. And here's one of the quotes from these guys, and this is like, two-phase commit is not fault tolerant because it uses a single coordinator. It's a single point of failure, and it's synchronous with a blocking approach to it. there's loads of problems with it. It's a really bad way to design. Consensus-based algorithms are significantly better, give you better performance, better resilience, better qualities of service that we need for this. So we think about different protocols for it, yet we keep asking for these same stupid things over and over again. And we kind of bait things into doing the wrong sort of stuff. So particularly, I find in this space is any protocols that require arbitration, it's the kind of command and control mindset. It doesn't tend to work. It's much better having that mindset. So think about Solly Floyd's idea with scalable, reliable multicast, using timers to go off, getting consensus across stuff. It's a much, much better way to achieve these things. You actually get greater performance out of it. Another favorite is guaranteed delivery. Like, what the hell does this mean? And again, it's making the problem someone else's. It's like pushing things away. It's terrible sort of human behavior. And the way to think about it is all applications need to have their own feedback and recovery things. You can't just tell the underlying transport or whatever, you're going to totally take care of this, because there's so many edge conditions, there's so much that can go wrong in this. We have to think about it. And how do we think about it? How do we deal with it? We start thinking about it by protocol layering. Because you happen to know that your transport does something in a certain way, you start relying on the implementation. That's breaking the contract. You've got to be relying on the behavior, not the actual implementation to do this. And so, for example, if you're communicating between two systems, you have your own protocol that say you give monotonic sequences to your messages. You can tell there's gaps. You can deal with idempotent delivery. You can deal with all of this at the right sort of level. Trying to make it a problem of the transport is kind of crazy. And we've got people who are even enabling the bad behavior. Like, I was really shocked whenever the Kafka folks were saying, we're going to give you guaranteed once delivery. It's like, no, it's been proven to be wrong so many times, but yet we keep going forward with this. Again, let's show our disgust a bit more. So let's wrap up here. Like, our protocols some of the most significant things we have come up with as humans? I kind of argue that they are. And I'll give you an example of one thing that would come up as an example. Anybody know this protocol? Scientific method. Probably one of the greatest things that we have discovered as humans. But at its core, it's a protocol. Led us to things like this. Famous photo 51. So what was happening with this protocol is, how do we encode information in sort of our cells? So Crick and Watson sort of went, how is it? So their question was, how do we do that? Their hypothesis was, we think it's done in a helix structure. Okay, what's the experiment to do that? Well, if we use X-ray diffraction, we should see the X. They performed the experiment. That's the result of it. They're able to conclude, because of what they knew about molecular interactions, this is a helical structure. How good is this from an evolutionary perspective? Well, it looks like we can encode about 2.2 petabytes per gram. That's pretty impressive tape and store stuff. So this is some pretty cool stuff out there. But it comes from our protocol. So Newton defined the protocol for how we do this. There's much more detail to this. Like, so you're going to do science, you're going to do single blind, double blind, triple blind protocols and how we deal with stuff. We do really amazing things when we apply them correctly. Like medicine, science, engineering, many things have advanced to a really good level because they take protocols seriously. So some of this is kind of my call for, if we're going to grow up and get better as an industry, we have to take protocols more seriously. And actually, protocols are the essence of ethics as well, because ethics is how we encode some of this. So I kind of like ask, why do we not take this more seriously? Why are they not studied and practiced more? I find people have heard the terms. We even get misled. Like, Google talk about protocol buffers. They're not a protocol. They're a codec. Like, us as an industry, we do terrible things. So I'll leave you with one thing to think about. On your next project, your first step that you go to do is your first step to install all of your favorite frameworks and tools and do whatever. Or do you actually start thinking about, what is the domain of this problem? And what are the protocols of interaction? What are the domain events that I'm going to start dealing with? And start from that perspective, seeing what you get out as a result. It's a different way of thinking, rather than just being tool and framework oriented and playing with the latest thing. And sort of try to discourage some of the really nasty tools. And on that, I'll thank you very much.